Section 8.7 covers a reaction that we call hydroboration-oxidation, and you can probably guess by the name that it's a two-step process. Hydroboration-oxidation adds a hydrogen and a hydroxyl, so we're basically adding water to a molecule, but with anti-Markovnikov regioselectivity. So if you remember the acid-catalyzed hydration and the oxymercuration-demercuration reaction, you'll remember that both of those proceeded with Markovnikov regioselectivity, but hydroboration-oxidation proceeds in the opposite fashion, so with anti-Markovnikov regioselectivity. So what happens in essence is that the hydroxyl ends up on the less substituted vinylic position. So this is the carbon that has the most hydrogens attached to it, and that's the carbon that's going to take the hydroxyl. Again, it's very important that this is a two-reaction sequence. So step one is we use BH3 and THF, and we call BH3 borane, so it's borane and THF. THF is an acronym for tetrahydrofuran, so I can draw what tetrahydrofuran is. It's this cyclic ether, and I'll talk more about that reagent later. And then in step two, you should recognize both of these, hydrogen peroxide and sodium hydroxide. So again, hydroboration-oxidation is a two-step process. So first you would take the alkene, step one, you would treat it with borane and THF, and then in step two, you would treat it with hydrogen peroxide and sodium hydroxide to achieve anti-Markovnikov addition of water across that double bond. When I do hydroboration-oxidation, not only is the reaction regioselective in that it proceeds with anti-Markovnikov regioselectivity, it's also stereoselective in that the hydrogen and the hydroxyl are added in a syn fashion. And what that means is both the hydrogen and the hydroxyl are added to the same face of the pi bond. And you can see that's represented here in these two enantiomers, and that the hydroxyl and the hydrogen are both drawn on wedges. So that means they're both coming above the page or above the plane of the screen. Whereas the second enantiomer, you can see that both the hydrogen and the hydroxyl, again, they were added in a syn fashion. They were added to the same side of the pi bond. And that's why both of these bonds are drawn as dashes. I would not get any anti-addition, so I will not see either of the two products that are shown here below. The structure of borane, BH3, is similar to that of a carbocation, but without a charge. So the carbon in a carbocation is sp2 hybridized in trigonal planar, and the boron in borane, BH3, is also sp2 hybridized in trigonal planar. The boron atom lacks an octet of electrons and is therefore very reactive. In fact, one borane molecule will even react with another borane molecule to form a dimeric structure that's called diborane. This dimer is believed to possess a special type of bonding that is really unlike anything we've ever seen in previous chapter. It can be more easily understood by drawing the following resonance structures that are shown here. Just like the mercurinium ion that we saw in oxymercuration-demercuration, this is another one of those rare cases where we break a single bond when drawing a resonance structure. So careful examination of these resonance structures shows that each of the hydrogen atoms, which are colored in red and blue, is partially bonded to two boron atoms using a total of 2 electrons. So such 3-center 2-electron bonds, we sometimes refer to those as banana bonds. So what happens is that the diborane B2H6 has to be stabilized in an ether solvent so that an appreciable amount of borane is present. So what happens is the THF, tetrahydrofuran, donates electron density into the empty p orbital of the borane and stabilizes it. And that's why we write the reagent as BH3.THF. So the dot in the middle represents the stabilization of the borane by THF to produce this species. I won't ask you to draw the mechanism for hydroboration-oxidation, but each step should make sense to you. The mechanism of hydroboration-oxidation is mechanism 8.3 in our book. You should study it, but no need to memorize it. All of the steps should make some kind of sense to you. And you should take a look at the regioselectivity and both the electronic and steric considerations. We'll take a look at the sterics first. So the boron ends up on the less hindered carbon. So that's the steric consideration. So here's the less hindered carbon in this alkene, and that's where my boron atom ends up. And that boron atom eventually ends up being oxidized to the hydroxyl. Now, in terms of electronics, well, the attack of the pi bond triggers a simultaneous hydride shift. So as the pi bond attacks the empty p orbital of the boron, one of the vinylic positions can begin to develop a partial positive charge. This developing partial positive charge then triggers a simultaneous hydride shift. Then the trialkyl borane is going to be treated with hydrogen peroxide and sodium hydroxide in step 2 to form the alcohol. In terms of stereospecificity of hydroboration-oxidation, what you have to remember for our class is that the addition of the hydroxyl and the hydrogen occur on the same face of the molecule. So if I take this unsymmetrical alkene, my hydrogen and my hydroxyl can be added from the top of the molecule in an anti-Markovnikov fashion or to the bottom of the molecule in an anti-Markovnikov fashion. And what I would end up with in that case are enantiomers. So I end up with a pair of enantiomers. If I have one chirality center that's formed, so again, I'm doing the anti-Markovnikov addition using my hydroboration-oxidation conditions. When the hydroxyl is added, again, the hydroxyl can be added to either face of the molecule, and I end up with a racemic mixture. So we use this squiggle bond here to represent that there's an equal amount of both the dash and the wedge. This is just another example showing you that when two chirality centers are formed, you get a racemic mixture. The take-home message from this slide is that when I treat my alkene with borane THF followed by hydrogen peroxide and sodium hydroxide, it affects an anti-Markovnikov addition of water across the double bond. But the hydroxyl and the hydrogen are added in a syn fashion, meaning they are added to the same face of the double bond. And that's why both the proton and the hydroxyl are shown as dashes here, and why they are both shown as wedges in the second product. So what I end up with in this case is a pair of enantiomers.